are discussing periodic classification. Well, I would like to brief you, you understand that if you are given 120, 130 elements, it's not about placing them in rows and columns, mind you. It's not about placing them in rows and columns as it sounds to be to you, but understand that there is a great degree of seriousness involved in this. And I was always telling, and I wanted to tell you always till we finish this chapter, that please understand that it in fact stimulates research. Remember, it's not about placing these elements in rows and columns and you have done with your periodic table. In fact, I was telling you that the entire chemistry revolves around what? The periodic table. So in fact, the person who is actually good at chemistry is good at periodic table, or vice versa. You must understand this, right? It stimulates research. What do I mean by this? I mean that today, if you are framing a periodic table with the 7th period being incomplete, well, naturally the periodic table will be incomplete for the simple reason, understand that, in an atom you have infinite number of what? Shells. And each shell or an orbit proposed by Bohr is a period. Mind you that. Each period which we are seeing in a periodic table is a shell, is an orbit. You must understand. And we know that an atom has infinite number of what? Orbits. It has infinite number of orbits. So I can expect infinite number of what? Periods even in the periodic table. You must understand that, right? Since you have infinite number of periods in the periodic table, you can expect infinite number of elements being placed in the periodic table. You must understand this, right? So right now we are discussing, we are actually dealing with the long form of periodic table proposed by Moseley. There are earlier attempts which we are not interested because those are obsolete. The one which is where we are dealing now, right now, is the long form of periodic table, or we call it to be the modern periodic table, which has 7 periods, and the 7th period itself is incomplete. Understand that when the 7th period itself is incomplete, you have a large scope for research. That's what I say, it stimulates research, because a period is a shell, period is an orbit, so you have infinite number of orbits, infinite number of what? Periods, and 7th period itself is incomplete, so you can expect, right, several other elements being found out, and if you can find it out an element 30 years or 50 years from now, you have the position fixed in the periodic table. That's what I say, and its properties can be understood, right, well in advance. That's what I say, stimulates research. So even the periodic table is open for you if you wanted to go in for research. You must understand. So why I tell all this, why I brief you and remind you all this whenever I take up this particular topic is for the simple reason, don't make it trivial. It's not as trivial as you're placing all the elements in in rows and columns, and then you say that I have framed the periodic table. No, this periodic table is driven by laws, the schemes, laws, principles, and it's not your way or my way, because after all you have to maintain harmony. You have to maintain harmony. And when I say harmony, you please understand that there are some properties which repeat themselves at regular intervals. You must understand. In fact, I was also, let me remind you also, and also remember that you have n number of elements in the periodic table, 120 odd elements in the periodic table. And if you ask me what is the basic difference between all these elements in the periodic table, I can simply say it's nothing but size. So the fundamental thing is size. Why lithium has a set of properties, why sodium has a set of properties, why potassium has a set of properties? Well, I can simply say it's because of size. So size forms the most fundamental thing determining the mode of activity of a particular element. Mode of activity in the sense, all the properties shown by what? Elements, you must understand that. So everything is fundamentally atomic radii, you must understand that, right? So while defining atomic radii, I was defining, and you can't go in for one definition. I was proposing several operational definitions. You can actually see the previous class what I have done for you, right? And then we were discussing about electronegativity. Electronegativity is something which is told for what? Non-metals, and non-metals are placed to the extreme right of the periodic table. So electronegativity is the tendency to attract electrons towards itself when you are actually participating in bond. Ultimately, that periodic property, that's nothing but electronegativity, will be also repeating itself at regular intervals. You must understand. And what we are discussing in the previous class is basically electropositivity, right? Electropositivity is a language, is the word used for what? Metals. You must understand. Look into the definition of electropositivity. Just recollect Just recollect what I said. Just recollect, what did I see? What is electropositivity? Electropositivity is basically nothing but the ease. Ease. Ease is nothing but the easy to do something. And in this case, it's easy to remove what? Electrons from a metal, right? So what is electropositivity? It is the ease with which an element loses electrons, right? Loses electron. That ease is also viewed to be a tendency. So as electronegativity is a tendency, ease is also what? A tendency which doesn't have any units. You must understand that, right? So these are tendencies without any word, units, you must understand. So the ease with which an element loses electrons. Now losing electrons can be only done when the electrons are actually loosely held and they are relaxing. They are basically relaxing. The electrons are far away from the nucleus. So I get a sense that even electropositivity is a function of what? Size, that I was telling you. So understand that if you wanted greater ease, then the electropositivity is basically a function of size again. And if you wanted to have an exact relation, electropositivity is proportional to size. You must understand this. Right? So greater the size, greater is what? Electropositivity, you must understand. So in the periodic table, where are the biggest sizes in the periodic table? They are placed to the extreme left bottom. That is, I'm referring to the alkali metals and alkaline earth metals. So if you ask me which elements are more electropositive in the entire periodic table, it is nothing but the alkali metals and the alkaline earth metals, because they possesses the biggest sizes in the periodic table, and the electrons are actually far away from the nucleus, and the electrons in alkali metals and alkaline earth metals are basically relaxing. When they relax, it's easy to remove the electron. The ease is called what? Electropositivity. In fact, remember that for potassium, rubidium and cesium, the electrons are almost relaxing like hell. And if you do a small energy is just enough to remove the electron. So the ease is greater when the size is what? More. So ultimately, what is surprising to me, you can actually quote any number of periodic properties in this chapter. Right? Periodic properties like atomic radii. The second is what? Electronegativity. The third is what? Electropositivity. So what are all this? These are all periodic properties which we are discussing. And what is strange and common in all this? I would like to discuss even more periodic properties in the coming classes. But what is very strange is everything is a function of what? Size. So even the modern periodic law says the physical and chemical properties are functions of what? Atomic radii, you must understand. So everything again boils down to what? Size. Even electropositivity is function of size, and even electropositivity is directly related to size. If that is the case, if you look into the way we are dealing with periodic properties, first we are defining a periodic property, then we are actually making a relation, and then we go for the trend and we go for the applications. Right? I have made a function of it, and then I made a relation, and then if you look into the trend, as size decreases from left to right in a period, the size will decrease, so electropositivity will be decreasing. So which are the elements which possess the greatest degree of electropositivity? That's nothing but the extreme left bottom elements. They possess greater what? Electropositivity. You must understand that. As the size decreases, even EP decreases, you must understand. And size is decreasing from left to what? Right. In a group, from top to bottom, the size is increasing, so the electropositivity also increases. That's why you find the best elements which possess the greater ease to remove electrons are nothing but to the place to the extreme left bottom. That's nothing but the cesium element, which is belonging to the first group. It belongs to first group from top to bottom. That is the bottom element in the extreme left of the periodic table. Hence it is more electropositive. You must understand that, right? So that is about the trends. That's okay for your board exams, but how do we extrapolate this, and what are the questions asked in your JEE or the NEET is important, right? So in that thing, I was telling the basic application number 1, and if you actually recollect, this is what we were discussing about. And if you recollect application number 1, well, if you recollect application number 1, I was telling electrolysis. Remember that you have n number of metals, because electropositivity is a language used for metals. Other than metals, I'm not going to use anything, because for non-metals we use electronegativity and electron affinity. because they love electrons. But electropositivity is the ease of releasing electrons. So you're vomiting electrons. And people who are electron vomiters are nothing but metals. So I restrict my discussion as long as electropositivity we are discussing. That's only for metals. You must understand this, right? So remember, in the entire periodic table, you have metals. And you know, extraction of metals depends on their electropositivity. Remember that, right? Extraction of metals, or the metallurgy, or the extraction of the metal from its ore, all depends upon what? The electropositivity. You must understand that, right? So in the extraction of metals, if you actually see extraction of metals, you have several procedures. And why several procedures? Why one of them is not useful? It all depends on electropositivity, and electropositivity varies in all the metals that are available in the periodic table. You must be listening to me carefully when I'm actually uttering these statements, sweeping statements which I'm making, right? So you must be understanding, and also imitate my language, what I'm using. You must understand, right? These are all the subject points. I'm not restricting this. I'm taking an integrated approach when I'm actually lecturing the topic. You must understand, I'm not restricting to a particular thing. I'm taking an integrated approach because you have done all this, right? So if you look into the extraction of metals from their ores, you don't have one procedure. You have n number of procedures. And all are functions of what? Electropositivity. Now if you look into this, the first one is basically electrolysis. This is electrolysis, which is basically a non-spontaneous process. It's basically a non-spontaneous process. The extraction of metals, you have n number of methods, some of them which I'm quoting. Why n number of methods? What is the basis for it? The basis is nothing but the electropositivity. You must understand the degree of electropositivity. You must understand that, right? And if you look into electrolysis, this is basically employed with metals that are extremely electropositive. When extremely electropositive, they are placed to the extreme left in the periodic table. So basically, I'm referring to the first group and I'm referring to the second group, and these are exclusively extracted, right, through what? Electrolysis. So that might be itself a question, which of the following metals are extracted through electrolysis? And in the options, you are actually search for what? You need to search for what? Alkali and alkaline earth metals are the most electropositive element. That's nothing but alkali and alkaline earth metals. You must understand that, right? So that's electrolysis. Second, you have the other ones, which is pyrometallurgy. Pyrometallurgy, right? It's pyrometallurgy. Pyro representing higher temperatures, right? Pyrometallurgy, that is extraction of metal at higher temperatures. This is nothing but extraction of metals at higher temperatures, right? Extraction of metals at what? Higher temperatures. That's what is called pyrometallurgy. You must understand. Now, why? Well, to whom do you apply this? Most of them these are transition elements, and that is iron, zinc, and all. They are the best guys fit for what? Pyrometallurgy. You must understand. Why? Because they are not that electropositive as the first group elements. So we are actually having different methods for different metals, and all is depending on the degree of electropositivity. You must understand this, right? So alkali and alkaline metals, you have the non-spontaneous process, that is electrolysis. Right, for the transition elements, the best suited. Transition elements are lesser electropositive when compared to what? Alkali and alkaline earth metals, because from left to right, electropositivity decreases as the size decreases. You must understand that. Right, so you're listening to me carefully, because it's a spellbound lecturing. You can't blink your eye also. Please understand this. You have to listen to me carefully. Right, so if that is the case, that's pyrometallurgy. That's the most famous for iron and what? Zinc, etc. And then 3, you have even hydrometallurgy. You must understand. Hydrometallurgy, right? Hydrometallurgy. Now, what is this hydrometallurgy? This is used for further less electropositive elements, very less electropositive elements. That's what is hydrometallurgy is extraction. This is extraction of metals at room temperature. At room temperature, you must understand. This is extraction of metals at what? Room temperature. You must understand. And the best things at room temperature, what are you doing? That's nothing but gold and silver. And this is gold and silver are the best metals for what? Hydrometallurgy, you must understand. So electropositivity is a word exclusively used for metals, and extraction of metals are done by various methods. Why various methods, if you ask me? That's because of the degree or varying electropositivity which we actually find it in metals, and we extract first group and second group through electrolysis, and the transition metals mostly are extracted through pyrometallurgy, and the noble metals like gold and silver are extracted through what? The hydrometallurgy, that is extraction at room temperatures, right? So electropositivity plays a role in the way, the method you choose or customize to actually extract metals from their ores, you must understand, right? And that's what is the philosophy or the basic things you must know while writing your exam. You just can't stick to the definition of electropositivity and then go on and write the exam. It's not possible like that. You need to integrate everything from the extraction to electropositivity. You have to link it up, and that's how the preparation must be for your exam, right? And what I'll do, if I actually go into the depth of electrolysis, you must understand this, right? You must understand this, right? Watch carefully here. When we actually see electrolysis, if you see electrolysis, this is the first group elements and this is the second group elements, and this is most suited because these are more electropositive elements. But you should be careful here, and remember that it's again electropositivity which will determine which metal is deposited at cathode and anode. Because when you actually say electrolysis, something is deposited at cathode and something is deposited at anode. This is what we need to discuss in electrolysis. It's all about cathode and anode, which element is getting deposited at what time, and all these things, how easily, and all these things we discuss. So at cathode, I think a cathode is minus, negative, and this is positive. Well, you understand that cathode is negative means it's an electron-rich substance. It is basically electron-rich substance. You understand, suppose if there is a competition between in the electrolysis tank, right? If you have H plus, Na plus, K plus, Rb plus, and Cs plus, all in the same tank. Understand this. All in the same tank you have it. All in the same tank. Well, the positive charge and all these is a sign of electron deficiency. It is a sign of what? Electron deficiency. And then what we are doing is when you switch on, all these fellows should run towards cathode. After all, the positives will run towards what? Cathode. So there is a competition to run towards cathode, eat the electron, and then stabilize yourself. You must understand this, because positive charge is a sign of electron deficiency. Negative charge is a sign of electron richness, right? So when you switch on, all these fellows are running. They all run towards the cathode. Which is the negative. And you know why people run towards cathode is for eating electrons. And the fellow who is more hungry will reach cathode first. And if you look into the hunger, trend, I think the order of deposition, if you see order of deposition, if you actually see, the hydrogen will deposit first, and then comes sodium, and then comes potassium, then comes rubidium, and then comes cesium. You must understand. So it is first deposited, and that is last deposited. You must understand this, right? I think it's a common sense, because it's all about electropositivity again. When that reason for that, then I think I can just put it in a box and write down for you that more electropositive deposits last. More electropositive species must be depositing last, and I'm not surprised about it at any cost. Because for the simple reason, you're more electropositive, then you're more vomiting electrons rather. The ease with which you vomit electrons is electropositivity. And you're vomiting, you have no crave for eating. I think it's a common sense, right? So I think the cesium is the most vomiting electron radical over there. I think since it is vomiting, it has no hunger. So I think it will be depositing last compared to hydrogen. I think its least electropositive, it deposits first, right? If that is the case, what is the nature of the question that is asked? That's important, right? There is a philosophy, but what is the correct question which is asked? Now the question asked is basically this. It's basically this. Please understand that aqueous NaCl, suppose if you take, this is called the brine solution. Aqueous NaCl is nothing but NaCl and water. That's nothing but the brine solution. When you take and go for electrolysis, it is hydrogen that is deposited, or the hydrogen gas that is liberated at cathode. and not sodium. It's not sodium. That's Nelson's process. That's for preparation of sodium hydroxide. You never get sodium. So it looks strange for people who do not know the subject point. They might think that when you're going in for the electrolysis of NaCl, aqueous NaCl, you're supposed to get sodium at cathode, which is ridiculous. You know the subject points, then you should understand that you get hydrogen instead of sodium, because sodium is vomiting. And it has no crave for what? Electrons. So it deposits last. It's always the hydrogen which is coming. And where does the hydrogen come from? Because it is aqueous NaCl, that's NaCl plus water. Right, from this you get the hydrogen which gets deposited first. You must understand. So you must be clear here. You must be clear here. Well, I can make a sweeping statement for you. Right, this sweeping statement, I draw the attention of everyone. I just say the sweeping statement, what I can make is, whenever you electrolyze the aqueous salt solutions of both the first group and the second group, both. Aqueous salt solutions, whenever you use for electrolysis for both first group and the second group, I think it's always a hydrogen which is liberated. You will never get the alkali and alkaline earth metals, you must understand. Well, this subject point you and me are discussing now, but at that point of time, this fellow knows this. This fellow knows that. It's down. It's Down's process. His name is Down. And Down's process, that's why he says he takes molten NaCl. Molten NaCl. Molten NaCl is nothing but the sodium chloride reaching its melting point. It's got melted. You don't have water here. You don't have water here. I think you can have the sodium getting deposited at what? Cathode. That's for sure. So in Nelson's process, we use molten NaCl, and sorry, I withdraw. It's not Nelson's process. It's Down's process, we use molten NaCl, and in Nelson's process, we use what? Aqueous NaCl. You must understand. In aqueous NaCl, it's hydrogen that is getting deposited at cathode, and in Down's process, I think it's the sodium which is deposited. So the sweeping statement you must be knowing is, whenever you're going in for the electrolysis of aqueous salt solutions of the both alkali and alkaline earth metals, it is never an alkali metal which is deposited at the cathode. Rather, it's hydrogen. That is the subject point which I need to quote. All these are nothing but electropositivity. You must understand that. That's application number 1, which is for you. So I now go for application number 2. Let's go for application number 2 now. That's application number 1, deposition. The order of deposition in the first application is a function of what? Electropositivity. You must understand. Let's go in for application number 2, which is very, very important, asked in the exam n number of times. So I draw the attention. Please listen to me carefully without blinking your eye. Right? Now, what is that? Application number 2. Application number 2. Applications of what? Applications of electropositivity. You must understand. So if you look into this, I think I was discussing last time about reducing power. Reducing power. And reducing power. Now, what do you mean by reducing power? Suppose if I'm vomiting electrons onto you, right, I'm a very good what? Reducing agent. You must understand. So if I'm vomiting very easily onto you, then I think I'm a better reducing agent. You must understand this. So reducing power basically is again a function of electropositivity. You must understand. Greater the electropositivity, greater is what? The reducing power, because electropositivity is nothing but the ease with which you are actually vomiting electrons. Right? So if you're vomiting electrons with ease, I think you are a better reducing agent. You must understand. Right? If that is the case, then I think if you look into the exact relation, Rp is directly proportional to electropositivity. You must understand. Right? So EP is directly proportional to reducing power. Greater is the electropositivity. You can label that element to be a better reducing agent. You must understand. If this is the case, we were discussing that electropositivity is basically a function of size. And if you look into this, electropositivity is basically nothing but directly proportional to size. Then I think if you combine these two, then what I understand from this, even reducing power seem to be a function of size. And you must understand Rp proportional to size, which is even proportional to EP, or let's restrict ourselves to reducing power, that's nothing but size. You must understand this. Ultimately, you discuss any periodic property, it will be a function of size. And recollect what I was telling, if you have 120 odd elements in the periodic table, and if you look into the mode of activity of these elements, mode of activity I'm referring to their properties, They are all functions of what? Sizes. It all depends upon the size. Even the reducing power, which is one of the mode of activity, is also proportional to what? Size. If this is the case, then understand that in periods, the size decreases, so reducing power decreases, and in groups, the size increases, so the reducing power also what? Increases. You must understand this, right? It increases. You must understand, right? So that's how it is. That's a trend. Now, if that is the case, then I have a question for you, and I draw the attention of everyone because application number 2 has been asked n number of times, right? Watch carefully here. What is application number 2? Let me put it, the question properly for you. Observe, because this has been discussed in the last class, right? Watch carefully here. Theoretically, it is like this. Watch carefully. Theoretically, reducing power, watch carefully, reducing power is proportional to the size, and the size is proportional to electropositivity. All are in direct relation. Theoretically, all are in direct relation. Now, if that is the case, the biggest sizes are nothing but alkali and alkaline earth metals. Biggest sizes in the periodic table, which are placed to the extreme left, and left to right size decreases. If this is the case, then I can write, if I take the first group elements, if I take the first group, that is alkali metals, then I would like to say the lithium, if I write the size, then the lithium is smaller compared to sodium, compared to potassium, compared to rubidium, compared to the cesium, right? That is the size trend. The lithium has the least size. Then, if that is the case, then if I can write the electropositivity, then naturally this is in direct relation. That is how the trend must be, because everyone are in direct relation. Then if I go for the reduction power, then I think lithium must be the least reducing agent. This is for a theoretical sake. That's for a theoretical sake, you must understand. So there is absolutely no doubt, this is absolutely correct. This is absolutely correct. But what he will be asking, and you must not confuse yourself, there is absolutely nothing wrong with this. This relation is absolutely correct. This is also correct, this is also correct, this is also correct. So lithium having the least size, it must be having the least reducing power. Absolutely correct. There is absolutely nothing wrong in that. Now the issue is, understand this. Look into the statement what I quote over there. Look into the statement. Even though, and I want everyone's attention please. Even though, right? Even though lithium has least electropositivity and what? The smallest size, even though it has the least electropositivity and the smallest size, still, and I draw the attention. Look into this statement. If you just stick on to this, there is absolutely nothing wrong in this. This is 100% true. It's 100% correct. But here is a deviation which I am actually quoting it for you. Even though lithium has the least electropositivity, smallest size, still, mind you, still, lithium is a powerful reducing agent in chemistry. You must understand. And that too in aqueous solution. In solutions, In solutions that I would like to underline. In solution, that's a caveat. That is a condition. That is a caveat. You must understand, that is a caveat. Right? If you just stick here, then this is absolutely right. Even though lithium has least electropositivity, smallest size, still lithium is a powerful what? Reducing agent in chemistry. In fact, if you look into the reducing power, then it is actually the lithium which is greater than sodium, which is greater than potassium, which is greater than rubidium, which is greater than cesium in a solution. In a medium or a solution, lithium is the powerful reducing agent. Now it leads to a confusion. Because here you said the fellow who is small, the fellow who is least electropositive is least reducing. But this is actually not in a solution. Remember, this would be true, and this is not in a medium. Not in a medium or not in a solution. You must understand. This is theory. That's basically theory. You must understand. But in a solution, it is the lithium which is the powerful reducing agent in chemistry, and not the bloody sodium which has the highest what? Size. You must understand. Right? The size of cesium is the biggest in the periodic table, but compared to lithium, which is having the smaller size, is a better reducing agent, and we wanted to know why. Because this is completely opposite. The only caveat, well, I'm underlining here, is the solution or a medium, you must understand. In a medium, in a solution, it is the lithium which is the powerful reducing agent, and not bloody what? Sodium or potassium, you must understand. Now you wanted to know why? Let us give an explanation, and this explanation is asked in the exam so many times. Now the common sense is if you're writing your exam for 5 subjects, and in mathematics you scored only 60% out of 100. Only 60. But I think in all other subjects you got 100 out of 100. So you stand a chance of being first in the class. So the criteria for standing first in the class is not alone mathematics. It's not alone mathematics. This is like alone mathematics. This is alone mathematics. You must understand. If you stick to mathematics, alone mathematics, then that is a separate case. It's not a mathematics exam. It's a 10th class exam or 11th class exam. We are tested for 5 subjects. Even though you scored less in mathematics, if you score full marks in other subjects, you have a chance of getting first. Similar logic can be applied over here. I think there are several other factors for lithium which are playing a role in making it a powerful reducing agent, you must understand. And you wanted to know why? Yes, of course, yes. Let us explain this why. Observe carefully. Well, I would like to write the question first. This is the assertion. Lithium in a medium or a solution or an aqueous solution, whatever, right, is a powerful reducing agent in chemistry, and he wanted the reason. And let me tell you this. Why it's a powerful reducing agent, you must understand here. Now the issue is, it is simple. Now suppose lithium in aqueous solution. How do you say this? Now what you do is, if you take lithium, now it is supposed to be, we are supposed to remove electrons, right? This is vomiting of electrons. And you spend some energy, let that energy be E1. This is energy required to remove electron. Energy required to what? Remove an electron from lithium. It's tougher. It's actually tough. It's tough. And E1 is too high. Because removing an electron from lithium seems to be tougher because it is the smallest in size. Because this fellow is small in size. Electron removal, right? Electron removal seem to be what? A tougher job compared to cesium, right? And in the case of cesium, since it is bigger, I think you can easily remove electron from cesium, but it's tougher. But I didn't lose hope. Please understand, this is in an aqueous solution. But still, anyway, you have removed it. But the issue is, when the lithium is there in water, in the solution, right? In an aqueous solution, let us say water. Let's say water. Then what happens, since lithium plus, you formed lithium plus, right? This lithium plus is now in water. Then I think it is like this, LiH2O X times plus. You must understand. The lithium ion is actually surrounded by X molecules of water, right? And remember that when you are smaller, you attract greater number of hydrogen molecules towards you. And then this is what is called hydrated. If I can draw it for you. This is the lithium ion, and the water molecules are surrounding you. And this I call hydrated lithium. Hydrated lithium ion, you must understand. And in chemistry, I draw the attention, please. I make a statement here. Please. Smaller the cation, greater is the number of water molecules surrounded by it. And when someone is surrounding you, there is an attraction, there is a force, there is a love. There is love. When there is love, I think you release energy. It's exothermic. And that process of surrounding of water molecules onto a particular ion, positive ion or negative ion, can be called as hydration. And hydration is exclusively what? Exothermic process. So this is hydrated lithium and plus energy. And let this be E2. So you failed in the first step. You got 60% in mathematics. But in the second step, if you actually see, this released energy is E2 is so much greater than E1, and some energy is compensated because you are highest, but E2 released is so much that energy can be used for removal of what? Electron, because you have the smaller size, making lithium a powerful what? Reducing agent, you must understand. So how do you explain this? This is nothing but the highest energy required to remove electron for lithium is compensated by the way of its highest hydration energy, because smaller ones hydrate more. You must understand. Right? You must understand the smaller ones hydrate more, and lithium hydrates more and becomes heavy. But this process of interaction of water molecules onto a particular ion is purely exothermic, and exothermic reactions, right, they release energy, and that energy can be used because it is very tough to remove an electron. So all in all, this is the reason, all in all, making lithium a powerful what? Reducing agent in a medium or in a solution. You must understand that. So how do you write this answer? The answer can be written like this, right? The high ionization energy, that is energy required to remove the electron in the first step, is compensated by the way of very high hydration energy, which is exothermic, making lithium a powerful what? Reducing agent in a solution. You must understand this. So if he is asking, the assertion is like this: lithium in a medium is a powerful reducing agent in chemistry. The reason for that, the high ionization energy which is there in the step 1 is compensated by the way of very high hydration energy, making it a powerful reducing agent. You must understand. So in solutions, it is the lithium which is a powerful reducing agent and not what? Cesium, because the cesium ion is bigger, you can remove it easily, but the hydration energy seems for cesium seem to be very, very less, because smaller ones hydrate more. You must understand this. Right? So if I can write the trend for you and put it properly, it is something like this. Watch. So this is a question: why lithium powerful reducing agent in a medium? That's nothing but a solution. The reason for that is lithium, smaller, to remove an electron from this tough, high ionization energy. Very high ionization energy, which is not good for a reducing agent, but what to do? But what happens, since this is in a solution, the lithium ions actually react with X molecules of water. So LiH2O X times plus. This is the hydrated lithium. And here the energy is exothermic. And I can simply say, if you add these two, I think the overall reaction is exo. Overall reaction is exo. It implies that E2 is greater than E1, so it's compensating for E1, and E2 is greater than E1, making lithium a powerful what? Reducing agent. You must understand this, right? So you must understand this. That is how we explain this, right? Now what we will do after electropositivity, remember this is what till date we have discussed. The atomic radii I was discussing in detail for you. I was telling about atomic radii, and then I was telling about electronegativity. Then now I told about electropositivity. You must understand this, right? So atomic radii, electronegativity, electropositivity. If you ask me what are these? What are these you are discussing? These are nothing but periodic properties, and these properties repeat themselves at regular what? Intervals in a period. You must understand this, right? So in that process, let us go and discuss even one more periodic property, that is electron affinity. You must understand. Let's take the case of electron affinity. Electron affinity, you must understand. Now what is affinity? Affinity is basically, it's nothing but love. Affinity is basically nothing but what? Love. You must understand. And love for what? Love for what? Love for what? Love for electrons. Love for electrons. You must understand. That is electron affinity. You must understand this, right? Right. If that is the case, as we follow a sequence, we are following a sequence, and the sequence is you define first, and then frame a function, and go for the trend, and go for its applications. That's how it is. So it's time for defining, but affinity is something which is love, and love for what? Electrons. Now remember this term, electron affinity, along with electronegativity. Well, I would like to write electronegativity and electron affinity. These two are the terms which are exclusively told for nonmetals. These are for nonmetals, and nonmetals are placed to the extreme right of the periodic table. So if there is any language which we wanted to use for nonmetals, it is nothing but what? Electronegativity and what? Electron affinity. You must understand, right? If that is the case, what is electron affinity? If you can define, well, I'm defining what is electron affinity, right? Now what is electron affinity? It's nothing but energy released. Look into this. It's energy released. So when I say this, electron affinity is basically exothermic reaction. It's basically exothermic reaction. You must understand, it's exclusively exothermic. Because when you say love for electrons, so you're catching it. When you're catching it, you're doing it naturally. And when it's natural, I think energy is released. Similar is what? Electron affinity, it's love for electrons. So it's also catching, so it's exclusively energy released. You must understand this. Energy released when an electron is added to a neutral gaseous atom. So I wanted to underline everything here. For better understanding. It's basically energy released. It's never absorbed. After all, it's love. It's basically love. So it is never absorbed. It's energy released. You're not forcing anyone for accepting electrons. It's love. It's pure love. It's natural love. In natural love, energy is released. And when an electron is added to neutral, gaseous, isolated atom. That's the point here. So that's nothing but what? Electron affinity, right? And if I can give you a pictorial representation of this, then it is the, let's take an element M, which is basically a non-metal. And non-metals have love for electrons. They have tendency of accepting electrons. So when they have tendency, when they have the crave for electrons, why don't you put it? Why don't you put it? When you put it, they will accept it. They form M minus, and plus this is energy released. And this is basically exothermic, and this is nothing but what? Electron affinity, you must understand. That's nothing but electron affinity, you must understand here. That's electron affinity. Right? And remember, it's a common sense. The common sense is the consequence of adding an electron is you already develop a negative charge. You already develop a negative charge, mind you. So it's basically, I call this to be first electron affinity. Because if someone is attempting, when someone is attempting M minus and add the second electron, then it would be difficult for you. Remember, it would be difficult for you, and if it is forming M minus 2, because you're adding an electron, because these two are repelling each other, because negative and negative will repel, and this is minus 2, and there now you need, it becomes energy absorbed. It is energy absorbed, and it is basically endo. And it is minus E. So basically what I'm telling is, the second electron affinity is endothermic. It is only the first electron affinity which is what? Exothermic. You must understand. You must understand this. Right? So, you should be very careful. You cannot be casual in reading definitions, man. You cannot be casual. Let us have a clear definition of what? Affinity is basically love. Love for what? Electrons. And then that's you, since it's a natural love for electrons, it's energy released. When an electron is added to a neutral gaseous atom, here is an atom, when you add an electron, you're getting M minus, then the energy is released, that's called the first electron affinity. But if you go for the second, you're already having a negative charge, then I think adding the second electron would be difficult for you. I think then you need to supply energy, that's nothing but what? Endothermic reaction. When I suggest this, people will ask me, well, what are you talking, man? You already have this. You have already this, and these are formed naturally. What are you speaking of? What are you speaking of? The oxide ions or nitride ions are almost available. If you say that energy is needed for the second and the third electron, then how are oxide and nitride ions formed? Is an issue. Or otherwise, someone can ask me even why F minus 2 is not formed. Or why F minus 2 is not formed, only F minus is formed. Whereas O minus 2 is formed, N minus 3 is formed. These are all the questions or the reasonings which crop up. And it's a common sense. Let's take the case of the oxide ions and N minus 2 and even take the case of what? F minus, you must understand. Before I go there, well, I'm discussing electron affinity. It's nothing but a periodic property, the property that repeats itself at regular what? Intervals. And electron affinity and electron negativity both are a language or the terms used for what? Non-metals, and you must consider only non-metals, you must understand. And it's nothing but the energy released. It's always released, never absorbed when an electron is added to a neutral gaseous atom, and it's the first electron affinity which is always what? Exothermic. From the second, third, fourth or n number of addition of electrons is always endothermic, right? If this is the question, then I think if this is what is the subject point, then people shall ask me this question immediately. The immediate question is if electron affinity is exothermic, if the first electron affinity is exothermic, second and so on are endothermic, then how O minus 2 is formed or N minus 3 is formed? You must understand. How O minus 2 is formed or even N minus 3 is formed. How are they formed is the issue. Well, I would like to take the case of what? The formation of oxide ion. Look into this. It's a common sense formation of oxide ion. This is the oxide ion. How that can happen? If the first electron affinity is negative, then how the say O minus 2 is formed easily? It's formed easily. And formation, in fact, I could say formation of oxide ion is extremely feasible. Yeah, of course, it's readily formed. Well, it's a common sense. If you actually see, O, this is a non-metal, then it expresses natural love for electrons. It's a natural love. So when I add an electron, it will catch, because after all, it's a natural love. You're catching on your own. Then it is O minus. And then it is exothermic. This is even. This is the first electron affinity. And this is absolutely exothermic. This is natural love. Right? But when you try to add one more, to this O minus, add one more, then it forms O minus 2, then you need to struggle because these two repel each other. It's repelling. So when you're adding, you're not catching. You're not catching as a natural love. Then you're not catching on your own, then we need to force it. When we force it, we need to spend energy. So it is minus E2. And this is endo. And this is the second electron affinity. When it is endo, then why is the formation of oxide ion extremely feasible? Well, it's a common sense. If you actually add these two, then you will find that this cancels. And you are left with the 2 electrons. If you add, then it is forming E minus 2. Right? And what is happening here, that the E1 is so much greater than E2, the natural love is so much greater than E2, then if this is 100 rupees, this is 25 rupees you have spent it. So the overall energy is what? Positive. And if you look into this, ultimately the energy is released is what? Exothermic. So ultimately the resultant energy is what? Exothermic. Hence the formation is what? Feasible. So even though the second electron affinity is endothermic, but still formation of oxide ion is very much feasible. Same is the case with even nitride ion. Same is the case even with the nitride ion. If you actually see, the case of nitride ion also is similar. Formation of nitride ion. If you actually see the nitrogen being a non-metal, the first love, a natural love, even this is exo. Since it's a natural love, exceedingly the energy is released. If you go for the second, then the repulsion starts. So N minus 2 is E2, which is endo. And the third one, N minus 2, and an electron will give you N minus 3, which is E3, again endo. The second and the third electron affinities are actually what? Endothermic. But if you add these three, then ultimately you will be left with N and 1, 2, 3, 3 electrons if you add. So you're getting N minus 3 plus exo plus energy. So the overall reaction is what? Exothermic. So formation of N minus 3 ion is what? Feasible. You must understand here. So that is the case. But I think people will ask me why F minus 2 does not exist. Why F minus 2 does not exist? If that is the case, then take the case of fluorine. If you add electron, it is adding, yes, you're getting it, exo. But what happens if you add one more, then it will form F minus 2. But if you add these two, then it is F plus 2E, giving rise to what? F minus 2 is what? Endo. It is endo, not exo. So the overall reaction is what? Endo. So it's not feasible. So F minus does not exist. Whereas O minus 2 exists, N minus 3 exists. You must understand it's a common sense. Even that way we can answer things or formations in a formation in energy terms also. Right? So what is electron affinity? Affinity is nothing but the energy released. It's always exothermic. It is never what? Endothermic. So it's always energy released when an electron is added to a neutral atom and it catches, and the more easily it catches, the more tightly it catches, it indicates greater love, greater energy. You must understand this. Right? Remember, I think the details and applications of electron affinity, which I will be discussing in the next class. But understand, periodic classification, as I am telling you, it is not that you have actually placed something in groups and what? In groups and what? Periods as you like. You must understand. It is not about that. Don't make it trivial. You cannot make it trivial. Remember why you can't make it trivial? I am telling you that each period on which the periodic classification has been framed is each period is viewed as a shell. Each period is viewed as a shell. If each period is viewed as a shell, then in an atom you have infinite number of shells. So you have infinite number of periods. And if you have infinite number of periods, you can expect infinite number of what? Elements. And what is very strange, till now, the 7th period itself is incomplete. So you can have infinite number of what? Elements being placed here. And it's an open for you. Even it open for you, you can bring out any element tomorrow, and I have a place in the periodic table even for you. That's what I mean by stimulating what? Research. So don't make it trivial, you must understand. Also, one more important point, whatever we are discussing, these are all periodic properties, and remember, each periodic property which you will be discussing is basically a function of size. Except size, you don't have anything. Remember, all the elements properties, whether it is physical properties or chemical properties or periodic properties or whatever properties, they are all functions of size. Mind you that. So even the modern periodic law says that the chemical and physical properties are basically functions of what? Atomic size and nothing else. That's how it is. We will go in for an applications of electron affinity basically in the next class and see it is also a function of what, and the applications which are important for the exam, right?